All right, so what we're going to start to do now is to look at the second phase of your NMR session. All right, and the second phase of the NMR session now deals with how to expand a spectrum in 2D, how to increase and decrease intensity, how to put the baseline at the center of the screen, how to do external projections, a bit about correlations, and then how to assign all your singlets in the end. Right, so we're going to tackle all of these things in this session of the course. Right, so I'm going to go to the NMR session, and I'm going to load my, I've already preloaded it, but you can also do it on your side as well. If you're following, you can load your TopSpin on your computers. Remember, this is freeware off the web that you need to install and to play with and to try and process spectra. What I'll try and do is also give you some experiments to play with. So I'll give you a full set of experiments, maybe 5 experiments, one for each of the different tasks that you'll be able to do. And you can actually play around with the program when you download it as well. I'll try to put that onto Moodle for you. Right, so I'm going to jump straight into the 2D stuff. Now remember yesterday when I was talking, I said I ran 5 experiments for a particular compound, and I saved it in my teaching portfolio. So my teaching portfolio under 751, because that's your module that I teach you for. And we looked at these 5 experiments yesterday. And keep in mind that experiment 10 had the carbon-13 NMR spectrum. Experiment 11 had the proton NMR spectrum. And we stopped there. So we analyzed 10 and we analyzed 11. We got a good grasp on how to analyze 1D NMR spectra. Today, we're going to introduce you to 2D NMR spectra. And I'm not going to say the simplest, but the easiest, I think, because it just involves one nucleus, the proton and a nucleus, is the COSY spectrum. And that's in experiment number 12. Right? So I'm going to display this and show you what it looks like. So this is a 2D NMR spectrum. Now, before I start, I want to explain very briefly what a 2D NMR spectrum is. A 2D NMR spectrum has correlations between the different protons in the molecule in this particular COSY spectrum. So I have on the x-axis and my y-axis the proton NMR spectra of the same molecule. So this is the proton NMR spectrum of that molecule that you see on the left here. That's also the proton NMR spectrum of the same molecule. And I'm going to look for correlations between protons within the molecule. All right, so some protons couple other protons. Now you see that because we had coupling constants that we worked with doublets and triplets and all of those things. So in order to get a doublet and a triplet, something will need to couple it, something will need to have an impact on the magnetic resonance of a particular proton and either subtract or add to it like we've done in undergrad. Now this spectrum just tells you where the correlations lie, all right? Now in order to analyze the spectrum, what I'm doing here, I'm just playing with my roller on my mouse, and I'm increasing the noise. You can see I'm increasing the noise here, and I can also decrease the noise. All right. Now, what does that actually mean? Imagine you are flying in a helicopter, and if you're flying in a helicopter, you're looking down, right? And I'm going to increase the noise like this. All right. Now, each of these small dots that you see would probably represent houses, the roofs of the houses. Right, so if I'm looking down from the helicopter, I can see roofs of the houses, and then I see other bigger spots. So you can see a big spot here, a big spot there, a big spot there. Those might be bigger structures, maybe tall buildings, right? So maybe all the high rises, all the tall buildings, I can see it here. So I want you to try and think in 2 dimensions now, or even 3 dimensions if you can, that these are structures pointing up. So these peaks that you're seeing, which are actually more pronounced than the other peaks, are the taller structures. And I can even go so far as to say that these peaks here, the one that are very pronounced, right, might be peaks of mountains, right? So if I had to maybe compare this one here with maybe this one here, maybe this is a very tall skyscraper, and maybe this is a mountain, right? And maybe this is the Drakensberg, where you have a series of mountains, right? So what I'm actually trying to get at is that each of these are peaks, right? So you're used to a peak in one dimension here, and that's a peak that you see in your proton NMR resonance. These are also peaks in a 2D NMR spectrum. And the more pronounced it is, the more intense it is, it actually means the higher the peak, or the greater the intensity of the peak. All right, so I'm going to now decrease this such that I try to, and I'm playing with just the roller on my mouse here, trying to decrease the intensity such that all the noise disappears. I just want to be interested in the more pronounced peaks, the high intensity peaks, because those are going to be the correlations that I'm going to look at. Now, there's a whole lot of peaks in this region here that I'm not going to even waste time on, because these are actually correlations between the impurities. Remember we said yesterday there was a lot of impurities in the sample, and all of these impurities, some of them have correlations with each other, and sometimes you're able to actually determine what the impurity is as well, but I'm not going to spend this session on that. So I'm just going to look at this particular part, because this particular part here has the correlations that I'm interested in, because those correlations relate to these proton resonances in the spectrum that you see here. So I'm going to expand this region and just concentrate on this particular region. And how I expand this region is, you can see the double cross here that I have with these black lines. I'm going to choose a point. I'm going to press down on my left button on my mouse, and I'm going to draw a square over the area that I'm interested in. And when I leave it, you can actually see now that I can very nicely see my peaks much more pronounced. And I can do the same thing here. I can increase the noise, or I can decrease the noise drastically, right? And as I decrease the noise, the more pronounced peaks will remain, and the less pronounced peaks will disappear into the noise, right? So it might be, you can actually say, as you go higher and higher in the helicopter, what is more pronounced? You can still see the peaks of the mountains and maybe some tall high rises, but you can't see the houses anymore, right? They'll be lost in the noise the higher you go. So if you want to look at it that way, right? So that's how you expand a 2D NMR spectrum, by using this crosshair and get the region that you want. Right now, there's some active buttons in a 2D NMR spectrum. Now, if I want to look at this y-axis here, and I want to make this active, I must click on that small square that you see on the left of your screen. So that small square makes that axis active. And I can now, after making it active, increase and decrease this particular spectrum, increase the intensity, decrease the intensity just by using the roller on my mouse, right? I can also right click, and when I right click, I can make the spectrum go at the center, right? So it might look a little bit better at the center. I can right click, and here you have the spectrum at the center. All right, I can bring it back at the bottom for you to see a bit clearer. I can do that as well, right? So whenever you want to play with the spectrum on this part, you need to have this active button here. And the same thing on the other side as well. I can now click on that particular spectrum and play with this particular spectrum. I can do exactly the same thing on this side, right? So bear in mind that if you want to alter the parameters or alter the intensities and put the spectrum at the center or the bottom, you need to click on those active buttons. Right, so I'm actually happy with how that is. Now I want to try and interrogate these peaks. All right, so before I even jump into this COSY spectrum, I just want to do a little bit history about coupling constants with you before I jump into this COSY spectrum. Right now, you've done doublets and triplets and everything else in your your lectures, I'm just going to take you through one of my handouts that I've made over the years. And this explains what a doublet of doublets is, right? So you're used to a doublet. So if I just have, if I look at HC being split by HV, just one resonance, and imagine these are not protons, that's a doublet. And I'm looking at the aromatic ring here. And if HC is split by orthocoupling here and another metacoupled here, I'll get a double doublet, right? And that will have two different coupling constants. We know it's 8 Hertz for this, and about maybe 3 to 5 Hertz for this. And a doublet of doublets would be when that splits that into a doublet, that splits that into a doublet, and that splits that into a doublet. So that's a doublet of doublets. And that would appear when all 3 protons split this hydrogen with different coupling constants. So you can see 8 Hertz, a 5 Hertz, and a 1 Hertz maybe, right? And you get a doublet of doublets. Now I'm going to look at this particular system, and I called it HX, right? Because HX, and I can show you just now what will happen with HX when HA and HB splits it, and then HC. But before I do that, I want to let you know that HA and HB are sort of similar distances away from HX, right? And they'll probably have a similar effect on HX, all right? And when they have that similar effect on HX, it probably splits them with very similar coupling constants. Now, I want to show you the effect of this. Now, have a look at this diagram here that I have. It's very badly handwritten. I have a signal for a proton. Imagine this is your HX signal, right? So that's your HX signal here that I have. So imagine this is your HX signal. And then I'm going to split it, right? I'm going to split it by the first proton, maybe HA, with the 8 Hertz coupling. And that, if you can imagine, it's 9 Hertz, right? And if the HB also splits the HX with 9 Hertz, can you see now if I have this line split by 9 Hertz and this line split by 9 Hertz, the line to the right of this peak and the line to the left of this peak will coincide in this particular region. So I'm not getting a double doublet as I should be getting. I'm getting what we call a pseudo triplet. So it's not a triplet, we call it a pseudo triplet because the two lines of either side of these two peaks here coincide. Remember that a true triplet would be 1:2:1, right? And in many cases, the pseudo triplet is not 1:2:1, it's some other arbitrary value, right? So we get a pseudo triplet in this case. So I want to take you back, if you can actually remember yesterday, but maybe I'll just take you back a bit and open a spectrum. I don't even need to take you back. You can actually see it here, right? So have a look at this particular resonance that we see here. See this triplet that we have here that looks like a triplet? This is a pseudo triplet, what I've just been describing. And this pseudo triplet actually comes about by what I've just been saying in this particular document. So these 3 lines here, there's a good example of what a pseudo triplet is, right? So this is actually a double doublet that you've seen and not a triplet. And then I'm going to take you one further. All right, so we've got a double doublet. You saw what it looks like, you know how it comes about. And then I'm going to have a small coupling, right? And the small coupling, so that's next to that 8 Hertz, it's a large coupling. That's next to that 8 Hertz, it's a large coupling. This HC is meta to the HX. So HA and HB are ortho to the HX, we get couplings of 9 Hertz. But HC is meta to HX. And being meta to HX, the coupling decreases to about 2 to 3 Hertz. And if I look at 2 to 3 Hertz, it's much smaller than 8 Hertz, so it's not going to overlap with anything. So you can see if I split each of these lines into a 2 Hertz coupling, a 2 Hertz coupling, and a 2 Hertz coupling, I can see each of these doublets. All right, so this is a doublet of doublets, right? A DDD, right? Doublets of doublets with coupling constants 9 Hertz and 9 Hertz. You saw how that came about. And the last coupling constant is 1.8 Hertz, right? Approximately 2 Hertz for the meta coupling. So you can see this sort of pattern that you can actually get. And this is what the peak looks like in a normal NMR spectrum. And I'm going to jump to the NMR spectrum, and can you see, if I'm looking at that particular NMR spectrum, can you see now this particular peak that I'm looking at? And that is your doublets of doublets of doublets that you're looking at here. All right, and I showed you how that comes about. All right, so the double doublet that you're seeing here is just split by an extra proton that I'm finding in this particular resonance. All right, so there'll probably be 3 protons around whatever's being split in this particular case, and 2 protons around whatever's being split in this particular case. All right, let's look further at that document. Right, now sometimes they appear distorted, so when the lines overlap, we can get various types of overlapping occurring, and sometimes you don't see it as neatly as we do. And why I chose this particular example to do the spectra on and to do my teaching on is because I can see these splitting patterns very nicely in this example, so I chose it. But in real life, everything is not just perfect like it is. You can't choose your example, you can't choose your molecule. So sometimes you get some things like that and some things like that. And I'll give you this document to have a read through, and you can see what you can actually expect from other doublets of doublets of doublets as well. All right, in the next case, which you won't see in this particular one, is what happens when I have a proton that's split into a doublet. The next one is split into a doublet, but one coupling constant is slightly smaller than the other one. So I still have 2 large coupling constants, but one coupling constant is slightly smaller than the other one. And to put that in context, maybe HA split HX with 9 Hertz coupling, but HB didn't split HX with a 9 Hertz coupling. It was something very similar, but maybe it was like 9.2 or 9.3 or maybe 8.5. Something different from the first one. And that's when you would actually get your doublet of doublets of doublets looking like this, where you see your 4 peaks. So here, these 2 peaks don't overlap. So you'll get a nice doublet of doublets that you can see. You don't get a pseudo triplet in this instance, when one is slightly smaller than the other. And if I take the small coupling constant in this case, which is a meta-coupled one, each of these peaks get split, right? So you can see very clearly that doublet, that doublet, that doublet, that doublet. So we can get a nice quartet of doublets that you're actually seeing here. But this is actually a DDD, right? A doublets of doublets of doublets that you see, right? And you can get various overlapping between this to give you various shapes of your peaks, various shapes and splitting of the different peaks that you get. And the last example that I want to show you is where you get 3 different types of splitting, right? So your first coupling, your second coupling, and your third coupling are very different. You can see 5.3 is very different from 9, and 1.8 is very different from 5. So I can see each split very nicely. And here I am sure to see my doublets of doublets of doublets very nicely like this. 4 peaks that you can see here showing like doublets, right? And they come about like this, right? So that's a DDD again, where each peak is split by or each proton splits the proton that we're looking at with a different coupling constant. And I can very clearly see my doublet of doublets, and I need to calculate my coupling constants. Right, so how do I calculate the coupling constant now? Because all I'm seeing is this. I'm not seeing it nicely like this. So here I can see it very nicely. There's my first coupling constant. I can see this is my second coupling constant. I can see this is my third coupling constant. But I can't see it so nicely here, right? So how we can actually approach this is work from the back. My small coupling constant will be very easy to see. There's my small coupling constant here, right? And the next smaller one is going to be this here. Now, if I break it down, this here is actually these 4 lines, right? So I can either take this first and this third peak, or the second and the fourth peak. I'll take the first and the third peak. I can take the first and third peak and find the distance between the first and third peak. And that distance will allow me to get the coupling constant of that particular peak, right? I can also get the bigger one as well, right? And note that in the bigger coupling constant that I have here, it's going to be a bit more difficult to see because now what I'm doing is I'm actually taking the distance between this peak here and this peak here, right? So it's the first and the third one now that I'm looking at. Because remember, if I had to split, if I split these to get these two different resonances, I'm going to take the middle of this peak here and the middle of this peak here, and then get my coupling constant. So all I'm doing is I'm shifting to the nearest line and shifting to the nearest line. So I can take the second line here, right, and look at the sixth line, and I can take the distance between the second line and the sixth line, or the first line and the fifth line, and get this big coupling constant here. Right, so I've got three coupling constants. I'll just run through that again. The small coupling constant is the difference between the first and second line. That's easy. The bigger coupling constant will be between the first and the third, and the largest coupling constant between the first and the fifth. And that's my three coupling constants for this particular resonance that I need to record. All right, why I told you all of those things is because we're coming back now and looking at this particular spectrum, and we're going to see what evidence we can actually get from this particular spectrum. But before we actually get to a spectrum, we need to look at a particular structure. And I'm going to look at the structure here because I have proton resonance. So each of these are proton resonances. And if I look at a typical splitting on this ring, this quinoline ring here, I'm looking at this aromatic ring. I'm going to first concentrate on this proton here, right on the top, where my cursor is. So this hydrogen now, let's see what it can be split by. Remember I told you yesterday fluorine also splits protons and carbons because it's NMR active. So this hydrogen can be split by this fluorine, and I'm expecting a large coupling constant of about 8 to 10 hertz because this fluorine is ortho to this hydrogen. I'm also going to expect a very smaller coupling constant, maybe about 2 to 3 hertz, with this meta hydrogen. Right, so I'm expecting a double doublet, and I can at some stage, in some instances, get coupling to this paraproton, but that coupling is very, very small, maybe like less than 1 hertz. So in many instances, unless your NMR spectrometer is very, very sensitive, we don't pick up that para coupling. Right, so we can, if we want to try and increase the sensitivity and look for that particular coupling, but in most cases, we don't see this para coupling. And if you do see a very small coupling, less than 1 hertz, you know that it's actually the para coupling. Sometimes it actually appears as about 1 hertz or 1.2 hertz or 0.8 hertz, right? But in many cases, we don't see that coupling. So if I look at this particular proton, I should get a double doublet, and the double doublet I should get is one big coupling constant, one small coupling constant. And let's look at my proton spectrum that you're looking at here. Can you see there's a double doublet here with one big coupling constant, my first and my third line that I showed you a minute ago, and then my first and my second line with the smaller coupling constant. So my big one with the first and the third line is probably due to the fluorine and the hydrogen coupling. And the second one, the hydrogen and the hydrogen that's meta to it, is probably the smaller coupling constant that you see here, about 2 hertz. So this double doublet is highly likely to be this particular proton on this particular molecule. So I didn't have to look at any 2D NMR spectra to determine which this hydrogen is. Right? It's unique to this particular molecule, and there's no other proton here that will actually experience that type of thing. And then I'm going to jump to this hydrogen, right? So this double doublet here, I can tentatively, and I say tentatively because I need to find maybe a little bit more proof of that. If I can provide, the more evidence I can provide, the better it is, right? I'm going to jump to this proton here, and let's see what I get. This fluorine atom and this hydrogen atom are sort of very similar positions to this hydrogen. So I can expect a large coupling constant and a large coupling constant here. So I'm going to get a double doublet initially, and that double doublet can either appear as a pseudo triplet, or it can appear as a double doublet if one coupling constant is slightly smaller than the next. And I look at my NMR spectrum and I see I've got a double doublet here, but I've also got a double doublet here that's split by something else as well. And if I look at this particular position of this proton, I've also got a meta proton on here as well. And this meta proton here that I'm seeing is the one we just discussed just now, right? So we just discussed that one just now. And this meta proton will couple that pseudo triplet into a smaller doublet that you're seeing here. We just discussed this a few minutes ago. So this is a doublet of doublets of doublets, where we get a pseudo triplet that's coupled by the meta proton into doublets further, and you see this kind of splitting pattern in this molecule. So I can tentatively assign this doublets of doublets of doublets to this particular proton on my molecule. Now, this proton and this proton being meta to each other would be coupled to each other. Remember I said that that splits that into 2 hertz, and the same goes the other way around as well. And that's why you got the small coupling constant. So if you measure the small coupling constant to be 2.6 hertz, it means that this small coupling constant must also be 2.6 hertz. If you measure it to be 2.2 hertz, this must also be 2.2 hertz. All right, so you'll find that sometimes when you do the exact calculations, you might get 2.24 here, you might get 2.28 here, and some people say, okay, this is 2.3 and that's 2.2. That's not correct. They must have the same coupling constant because they couple each other. So we can take an average of the two and make them maybe 2.5, or you can sometimes, I tell my students to look for the more clearer coupling constant and use that particular coupling constant as that particular value, right? Well, now it brings me to this particular spectrum. If these two are meta-coupled, I'm going to expect to see some correlations here. And that's how I read this particular spectrum. I go down to the diagonal, I look at the peak, I go across, and when I go across, I go up, and I see that it is coupled to this peak. So this square that you have here is actually the coupling for those two protons that we just discussed. So you can see nice correlations here. And I can very quickly correlate these two protons to see where is another proton that's in this vicinity. Remember that we have the meta protons here, but we also talked about another proton. So I can now do the same type of thing. I can run down to the diagonal and look for another correlation to see what else is it correlating to. And when I run down to my diagonal, I can see I have another correlation to this particular peak that I have here, right? Now, unfortunate for us, that peak is in this noise here that you see, right? But I can get another couple system here as well, right? So what I'm actually showing you is that I have a proton next to, so I'm using, if you look at what I'm doing very carefully and very cleverly, is I'm choosing this as my central proton, right? And I know that that's this proton here, this hydrogen here. I know it's next to this hydrogen, and I know it's next to this hydrogen. I know which this hydrogen is tentatively, right? So that's why I say I've actually got something like this to show you that proton. And then I want to try and look for the other proton now to see if there's correlations, and I can see another set of correlations here. So this system, this proton-proton system that I'm seeing here must be due to this particular proton here. And unfortunately for us, I can't see it very clearly because it's in this noise here. But if all the other peaks, you know, disappeared, I would very easily see a nice double doublet for this proton here. And that double doublet would be very similar to how this looks, right? It might be slightly higher, I think, from experience. This fluorine couples this proton with slightly higher coupling constants, but it would look exactly like how this peak looks here in this mess, right? But you can't see it because there's overlapping peaks here, right? So we can probably identify this proton as somewhere in this overlapped peaks, this proton as this triplet of, or doublet of doublets of doublets, and this proton as this double doublet. And these are COSY correlations to show you that they do correlate to each other. All right. I'll do one more correlation in this particular instance. And I'm going to use this triplet that I have here. Now, this is a pseudo triplet like what I've just indicated when I've discussed this with you. And if I look at the pseudo triplet, it means that I need protons that next to each other and also has a system that there's no other protons affecting it, all right? If I look at this other aromatic ring, and I'm jumping straight to the other aromatic ring because I've dealt with this aromatic ring here. I'll look at this in a moment and I'll look at that in a moment. I'm jumping to this aromatic ring here because I know in this particular case, I've got a fluorine atom that will couple each of these protons here, right? With a large coupling constant of about 8 Hertz. And next to these protons here is also these two protons that are equivalent, which will also couple those with a large coupling constant of about 8 to 10 Hertz. So I'm looking at two very large coupling constants coupling these two protons that I'm seeing here. And that's why I'm getting a pseudo triplet that's appearing here. Right? So that pseudo triplet appears here because of coupling to the fluorine and coupling to these ortho protons that you see in this region. All right? So it's a double doublet again, but appearing as a pseudo triplet, coupling to the fluorine and coupling to the hydrogen. So I've identified these two protons here. And since these two protons are coupled to these two protons, I'm expecting to know where these are. Now, ordinarily I'd get a nice double doublet for this, and in some other spectra you can see the double doublet very clearly. All right, you can't see it very clearly in here because see what happens when I look for correlations. That protons must also be in this noise, right? You can see there's my cross peaks here, and you can see it's coupled to something that's in the noise as well, right? So it's coupled to something that's in the noise here, which means that the double doublet for these protons must be in this region here. I don't see the double doublet nice and clearly because it's coupled into the noise. If you could see it nice and clearly, this is a very a nice example because when you see some other spectra, you see it very clearly as a doublet of doublets with an 8 and 5 Hertz coupling. So you can actually clearly see the double doublet in this case and not a pseudo triplet, right? And it's coupled to 8 Hertz with the ortho proton and 5 Hertz with this fluorine atom. So you see a nice double doublet, which is slightly bigger than this double doublet here that you see, right? So we can actually see that in further examples. So I know that this is those two protons. I know that this is this proton here. I know that that is that proton there. I also know that in this mess here, I have 1, 2, the equivalent. So I've got 2 protons in there. I've got a third proton in here, right? And remember yesterday we said there were 5 protons in here. So we identified 3 of the 5 protons that's in this mess. Let's see if we can find out what the other 2 are. And let's see if we can find out what these 2 are. All right, so we've got these 2 left here. So I'm going to take this smaller coupling constant first. Now I need to know something about trans olefinic protons, and I think I've taught you this in undergrad as well, that when you have a double bond and protons trans to it, what happens is that the cis coupled protons couple each other with a coupling constant of 8 Hertz, and the trans protons, like you're seeing here, couple each other with a coupling constant of 16 Hertz, which is twice as large as if it was cis. So if it was cis, it's 8 Hertz, and if they trans, it's twice as large. And if I look at this peak and I look at this peak, right, and if you go to your proton spectrum, you can probably calculate the coupling constant. In fact, let's do it now. So I taught you how to manipulate these spectra yesterday, so you must be very good at doing all of these things. You can see how fast you need to do it. And let me look at the small one here. I've got an 8.2 Hertz coupling. Let's look at this big one here. I've got a 15 Hertz coupling or a 16 Hertz coupling in this particular peak. So this coupling constant is twice that coupling constant. All right? So that coupling constant is twice that coupling constant. I can immediately identify this peak as either that proton or that proton, and I can identify that peak as either that proton or that proton. Now this doublet could very well be one of the other protons on this molecule as well, but you see that we analyzed this such that we had no doublets in this particular ring and no doublets in that particular ring, right? All had some complex splitting patterns that you've seen. right? So it's highly likely that these two pairs of doublets, this is one of them, the other one must be in the ring. And in these two trans-olefinic protons, this is one of them, the other one must be in the ring. So let's see if we can confirm that the other one of this is in the ring and the other one of this is in the ring as well. And we saw how to do that, but let's just do it again for these two, just to put our minds at ease. Right, so there's the spectrum that I have here. And now I'm going to look at this particular resonance and this particular resonance. All right, so let me take this particular resonance first. As I said, I go down here. And can you see my correlation here? The correlation is to something in this overlapping region, which means that the other doublet must be in that overlapped region as well. And let me look at my big coupling constant. I'm going to go down to the diagonal. Can you see that box that I'm making here? Which means that the other proton of that particular or coupled to that particular resonance is also in this particular overlapping of peaks that we see here as well. So I've identified all my 5 overlapping peaks as in this overlapping peaks that I'm seeing here, roughly between 8.1 and 8.3, right? So this region here. So that's how you use a COSY spectrum, right? So you see up until now, I didn't use my 2 nuclei 2D spectrum. I just used the 1 nuclei 2D spectrum, which was the COSY spectrum. And I was able to get a whole lot of information about this just using coupling constants, just using chemical shifts initially, because you know this is the aromatic region. So all these peaks are in the aromatic and olefinic regions. So I just used the coupling constants, my chemical shift, and my splitting patterns very importantly. So this is something new to you that you don't really do in undergrad studies, right? So these coupling constants that you learned and these complex splitting patterns give you an indication of what this is, what that is, what that is, what that is, and what that is, right? So you're able to get a whole lot of data from this particular spectrum, right? So that's the COSY spectrum that you are looking at. I'm going to take a short break, maybe 5-minute break. It's 2:47 now. We'll come back at 2:55. And when we come back at 2:55, I'm going to start with the HSQC and HNVC spectra, and I'll show you how to finish up the structural elucidation of that particular molecule. Is there any questions that you have for me before we take a short break? Is everyone familiar with what's going on? It might be overwhelming at first, but this class is quite good because I see you got the grasp of it yesterday. So I think you'll probably be able to handle anything that you get your way. So I'm going to take a short break now. If there's no questions, I can't see any hands in the room. And we'll start again at 2:55. Right, so I'll see you just now.